Yep. All right, here we go. Question 2, 2019, last year's AP Calculus AB exam. Remember, this is a question where it was intended to be done with a graphing calculator. So your question that you take on this year's exam, you won't have a question like that. Again, you might be asking why go over it then, because there are some awesome concepts in this question that you will be tested on, but just maybe in a slightly different manner. So this is a really good question. I hope you try this on your own before watching this video, before Google searching the free response guidelines, which takes 2 seconds to do, right? So hopefully you're not just doing that. All right, so here we go. So you got a table of values. It looks like a velocity function here at different time values. So I'll read it. Velocity particle P moving along the x-axis given by the differentiable function. That's huge. So they're telling us that V subscript P of T, so Vp of T, is differentiable. All right, so that right off the bat, you should be thinking, oh, it's differentiable. Then I also know it's continuous, right? So that's a big deal. It gives you the unit, meters per hour. T's and hours, selected values are given. And then this is another huge little bit of information. It says that particle P is at the origin at T equals 0. All right, so let's kind of break down some stuff that they're giving us here. All right, so first off, the fact that the particle is at the origin at T equals 0 means that the position function, which a lot of times we denote x, right? If V is velocity, then position would be x. It's a little annoying, but I should do the subscripts here since they're going to introduce another function later on. All right, so that would be my position function. And it said it starts at the origin at 0, so that would mean that x of 0 is 0. So that's an initial condition right there. Also remember that it told you that Vp is differentiable. All right, so those are all two big, huge things. So it says, all right, justify why there must be at least one T in this closed interval at which the derivative of the function they gave you, velocity, which you know, they didn't have to tell you this, is the acceleration, equals 0 meters per hour or meters per hour squared, all right? So it looks somewhat confusing, but it's really not. So let's just backtrack a second. So I'm going to show you some work that is not a part of the solution to this question. This is just for note flavor here, all right? So do you remember do you know what theorem I'm going to say? Hopefully you do. The mean value theorem, which basically says, all right, if you have a function that is continuous and differentiable, so it's smooth, on some closed interval, a, B, what can you say? Well, we know that the slope of the secant line over that interval, which would be that green line right there, the slope of that green line, there must be at least one spot within the interval, call it C, call it T, call it whatever. Usually we call it C, all right, not dot, C, all right, where the slope of the tangent line at that point is equal to the slope of the secant line, okay? And this is for some function, say, we'll call it y equals f of x. So a couple things here. In order for you to say this, you need to know that f is continuous on the closed interval, AB, and that f is differentiable on the open interval, AB. Like this is the hypothesis. This is the if part of your theorem. This has to be true. If that is true, then you can state the conclusion, which is therefore there's going to exist some C in the open interval such that, and here is the big to do, such that the derivative at that C value is equal to the slope of the secant line over the interval, all right? That's your mean value theorem right there. You might want to put that on your little summary sheet when you're taking this year's exam, okay? So, all right, first off, what is this in layman's terms? Because this seems so confusing, but it's really not. Think about this as if you go on a car trip, right? And you average over the length of that car trip. Say you go to Indiana and you average 80 miles per hour on your ride to Indiana, right? That's your interval. What do you know had to have happened at least one point during that car trip, right? Your instantaneous speed at least one point had to be 80 miles per hour, right? That's the mean value theorem. It's pretty simple stuff, right? Where the secant line represents, the slope of the secant line represents average rate of change, and the slope of the tangent line represents instantaneous rate of change. Now, I've told you this in the past in that a lot of times, all right, we view the mean value theorem where a function is f, right? And then, our derivative is f prime. But, just not that it happens here, but this generalizes for whenever the relationship between this function here and this function here, right? This is the derivative of that. It's basically what I'm saying. So in other words, if I would have changed this, I'm going to have to hit undo a bunch of times. So I don't want to mess people up. But if I was to change this original function to be f prime, then all of this stuff would be true. I'd have to check that f prime is continuous and that f prime is differentiable. And if it is, then the slope of the tangent line on f prime, which would be f double prime, would be the slope of the secant line over that function. So notice the deal here. This is one derivative away. So you can do that. I can call this f double prime. These would be double double. Then this would be triple. That would be double, and so on and so forth. All right. So that's kind of the story there, and you have to be able to apply that. So now, not that we need to get too confused with the primes here. They started off in a sense with a prime, right? They started off with velocity. So now instead of calling this f of x, this is like vp of t. Okay. So long story short, let's see if we can apply this to this question. First off, the hypothesis. All right. The function we're doing this to is right here. So do I know it's continuous and differentiable? You do, and you have to state why you do. All right. If we go back to this right here, it tells you given by the differentiable function vp. So that's huge. So the fact that vp is differentiable, right, that implies that it is also continuous, okay? The converse of that is not true. If you're continuous, you're not necessarily differentiable, right? Just think of corners and cusps. But if you're differentiable, you must be continuous. So you'd state that. You basically say, hey, VP, right? VP is differentiable on the open interval 0.3 to 2.8 and continuous on the closed interval 0.3 to 2.8. Okay, so there is your hypothesis. So if that's the case, then you should be able to state the conclusion. And the conclusion is, therefore, there's going to exist instead of calling it C, since they're asking us to call it at least one time T, therefore there exists a T, right, in this open interval such that the derivative at this T value is equal to, now I did F, right? I shouldn't be doing F. I'm a chucklehead, right? What should I be doing? That's Elvis going bananas. All right. Such that the derivative of this given function, right, which would be the acceleration function, is going to equal the slope of the secant line over the interval. So VP of 2.8 minus VP of 0.3 over 2.8 minus 0.3. And you basically would just rock and roll here. So you'd say, all right, V prime of t, there's got to be at least one spot where, all right, let's do this. How would I do VP of 2.8? I look it up in the table. It's 55. Well, take a look. VP of 0.3, that's also 55. So that's good news for you. So you get 55 minus 55 is going to equal 2.8. That's going to be 0 over 2.5. So it's going to be 0. So there you go. So you basically proved it and you justified it. Okay. So really not too big of a deal there. All right, let's rock and roll. Let's go to the next question. Oh, and this is by the mean value theorem. So honestly, I would say, this, and then I would write, maybe right above there exists. I would write, by the mean value theorem. Drop that little name bomb right there. Okay. All right. Good stuff. So let's go to the next question. It says use a trapezoidal sum with the 3 subintervals. These are the ones in the table, by the way, to approximate the value of this integral. So you're like, all right, how do you do that? So let's just rewind for a second. Again, note flavor, right? If I had a function, which the function doesn't necessarily look like this, but if I had a function, right, and I was approximating an integral by drawing trapezoids under it, right, I would say If this was maybe one of my subintervals, call it AB, then the way you draw a trapezoid is you go up until you hit the curve, up until you hit the curve, right? And then you go across like that, okay? And then the area of that would be where you begin. Now, how do you find the area of a trapezoid? Area of a trapezoid, average of the bases times the height. So it's going to be 1/2 base 1 plus base 2 times the height. Now, let's kind of put this in calculus world. So, all right, you got the half. What's base 1 and base 2? Your bases are your parallel sides. So when you do these trapezoidal approximations, these things are your bases. So those will be your functional values, right? So in this case, if this was the function, say, y equaled f of x, then f of a would be my first base, and f of b would be my second base. All right. Now your height, right? You think height, oh, it's got to be, no, that's not your height. Your height is your distance between the parallel sides. So in this context, that's this distance here. That's b minus a, which I'm just going to call that, maybe you guessed it, your delta x. So that's your delta x. So that's how you figure out the area of a trapezoid in these situations. All right. So that's kind of like just a general thing there. So now if I want to do this problem, right, they gave me the functional values, right, for velocity. They went ahead and did that. So I'm basically going to do it with trapezoids. Now, in the past, I've told you, draw a picture with a table if you're unsure so you can see it. And you can do that here too, but you may get a little whacked out and confused because there's a negative functional value here, a negative velocity value. So your trapezoids don't really look like trapezoids. They look like triangles or bow ties, right? So that may confuse you potentially. So that's why I'm just not going to do it. And that's why I kind of drew this procedure here, because that's basically what you do here, right? So you basically have to find the area of the first, the second, and the third trapezoid. So this integral is going to be approximately equal to, let's go get them, 1/2, right? What's the first functional value on this interval? Well, let me go back here. It's 0. And my second functional value is 55. So those are my two functional values on that first interval. That's my f of a and my f of b over here. So it's 0 plus 55. What's my delta x? That's the length of this interval. That's going to be 0.3. So that would be the area of the first trapezoid. Now, it'd be a weird trapezoid, right? Because one of the bases is 0. That would be like starting here. So it's going to look like a triangle, but who cares? All right. It still works. All right. Plus, now I have to do 1/2. That looks like a 2 and a 2. That's supposed to be a 1. 1, 2. All right, 1/2. So now what are my functional values here? Well, in my next interval right here, my functional values are 55 and negative 29. Okay, so 55 and then plus negative 29. And then times the delta x. What is the delta x? The delta x is going to be the length of this interval. So that's 1.7 minus 1.3. That's going to be what? 1.4? All right, so times 1.4. And then I'm going to go plus 1/2. What are my next functional values? Well, let's take a look. So now I'm going to, right, here to here. So that's going to be negative 29 and then back to this 55. Okay, so all right, here we go. So negative 29 and then 55. And then the delta x here would be, it looks like 1.1. And that's it. And that's going to be your trapezoidal approximation for the net signed area under this curve between 0 and 2.8. Some of it's going to be above, some of it's going to be below. Notice I said net signed. And when you do this, when you crunch these numbers, you should get 40.75. So if you want to actually go ahead and sketch it out, plot it, and see what the triangles and the bow ties look like, you could. What the heck? Let's do it. All right, so let's just see what we're talking about now that we did it without the visual. Okay, if we have this, and there's what? There was 0, there was 0.3, there was 1.7, and who cares if it's the scale? There was 2.8, and even though we didn't do 4, I believe there was 4 over here, right? The functional value at 0 was 0. At 0.3, it was like 55. At 1.7, it was what? Negative 29. Then at 2.8, it was back to 55. And then I forgot, what was it at 4? It was at 48, even though that wasn't needed for this part of the question. So again, I'm sketching a curve here because I know the function's continuous, but you don't really know what the curve looks like, right? So maybe it kind of, I have it bottoming it out at these values. No one knows that. So this is just a rough sketch, just going through it. So when you go to do your trapezoids now on this first interval, well, I'm already touching the curve. So I'm not, that's it. I go up until I hit the curve. Well, that's right there. Here, go up until I hit the curve. Notice that first trapezoid, it's like a degenerate trapezoid, right? That's this guy here. That's basically going to be the area of that triangle. This is where it gets a little bananas. That's why I said this may have confused you. When you go to your second interval, up until you hit the curve, up until you hit the curve, right? Now when you connect across those, you get like this bow tie looking thing. Where you get like a little net signed area going on right there. Okay? So that happens there. That's also going to happen with this interval here. So from here to here, up until you hit the curve, it's really down until you hit the curve, up until you hit the curve. All right, connect those functional values, and you get that bow tie looking thing right there. So that's kind of what you're doing. And they wanted it from 0 to 2.8, not the 4, so I don't include that. Okay, so that's kind of what it would look like. And this, again, is the graph of V of P dt, and that's your T. Call this Y, call it whatever you want. All right, so I mean, that's why I said I didn't draw this, because this almost looked confusing. It was like the little snafu they threw in this question, but again, it still follows this procedure. You know, do you know the formula for the area of a trapezoid, and do you know how it applies to when you're finding using trapezoids to approximate net signed area, right? Where the functional values appear in parentheses. This is your delta x, and that's your 1/2. Okay, so hopefully you're good with that. All right, so easy breezy. Let's move on to the next question, which is this. It says a second particle, Q, also moves along the x-axis so that its velocity between 0 and 4 is given by, so they give you a function now in meters per hour. So, you know, the first part, they gave you a table of values for a velocity function. Now they give you a function, right? They're big on doing that. Let's show you how to do something numerically with just values. Now let's show you how to do something when you're given a function. It says, find the time interval during which the velocity of the particle Q is at least 60 miles per hour. All right, so you want to find a time interval for which the velocity of the particle is at least 60. So that's like the first part of this question. The second part is then find the distance traveled by Q during that interval. So obviously you have to get the interval correct, and then you'd find the distance traveled. So let's stick with the first part of this question right here, which is, how do I find out when the velocity of the particle is at least 60? Well, first off, what does that even mean, right? Think about it. You're trying to find out when VQ of t is at least 60. So it's greater than or equal to 60. All right. So basically, you would take this and put it in right there, and you'd have to solve that, right? So now you might be given a question like this on your test where you'd have to solve the inequality, which is basically more or less like solving an equation. You would not be able to solve this by hand. And remember, this question on last year's test was a calculator question. So to solve this, it's actually pretty easy, all right? All you need to do is graph the velocity function on the appropriate interval, right? Then graph 60, and then see when this is above 60, right? So hopefully that sounds pretty easy. So if I do that, and I'll just do it in Desmos, right? Here is my velocity function right here, okay? That's my VP of t. Here is 60. So if I want to figure out when this thing is greater than or equal to 60, I just need to figure out those points right there. Well, bam, all right? 1.866 and 3.519. On that interval, my velocity is always above 60, all right? And you were expected to do that last year with a calculator. Okay, so pretty simple stuff here. So if I come back in terms of showing work, it would have been done on your calculator, and then you just said, you know, t equals, what did I say, 1.866 to t equals 3.519, maybe better yet, write it as an interval. Okay, so simple stuff there. So that's part one of the question. Part two says, now find the distance traveled. So this should have been an automatic for you, right? You're like, oh, if I'm given velocity, I want to find distance. That's pretty easy. Again, maybe this is on your little summary sheet. To get total distance over some interval AB, do you remember what to do? It's the integral from A to B of the absolute value of velocity, right? If you take the absolute value away, you get displacement. all right, but they wanted total distance. So basically what I would be doing here is I would integrate from 1.866 to 3.519 of the absolute value of VQ of t dt. And this would be done in your calculator. That's how this problem was intended to be done. So that's like 106.108 ... Okay, meters. That's it. So again, if it's a calc question, I would have had this value stored. I probably would have stored this as alpha A. I probably would have stored that as alpha B, right? Maybe even on my work, say let little a equal 1.866, let little b equal 3.519, because now I'm storing all the decimals, and then I avoid this nonsense that I did over here, and I come over here, and now I actually do this from A to B, where I told the whole world what A and B were, and then when I FN int it in my calc, I'm using the exact values. You won't have to do that because your test isn't going to be designed that way this year. But this stuff you could be asked, right? You could be asked this question where you're going to be solving that algebraically, right? Might be simple. And then you also could be asked to do this integral where you actually can integrate it, right? This one would be a disaster for us to try and integrate, all right, by hand. But you might get one that is not a disaster. So again, that's why we're going over these. The concepts in here are huge. So hopefully you're okay with that. All right, so let's go on to the last question, which is another solid question. So it says, all right, at time t equals 0, particle q is at position x equals 90. So that's good stuff. It's a starting point now for this other function q, this other particle q. It says, using the result from part b and the function vq from part c, approximate the distance between the two particles. So it would make sense that if you can get the position of the two particles at this time value, then you would just subtract them. So let's think about the things that we have here. Let's kind of like organize our information. There's particle P, right? And then there's particle Q. What do we know about P? Well, one of the first things we wrote down was that the P started at the origin. So we know that initial value, right? Do we know a position function for P? Well, we never actually wrote that, but if we have the initial condition and we have its velocity, even though it's in a table, right? If you're given a derivative and you're given an initial condition, you should be able to write what the function is as an integral function. So you should be able to write that xp of t would equal the integral from something to t of its derivative, which is vp of t, right? That's that bread and butter stuff I always talk about. So now the fact that this equals that would tell you that if I integrated from 0 to t, right, I would get that. That's how that initial condition comes into play, because this is the net change in position from 0 to any time t, and there was no starting value. So then this will get you the position at any time t. So that's important. So now if I want the position at 2.8, right, think about it, I would do the integral from 0 to 2.8 of vp of t dt, right? But you did that in part, what was it, B? Right? You did that in part B, and we got 40.75. And they said that you can use that value because we don't have a function for this. You have a table of values for velocity, so it's not like you can actually integrate anything. So you're going to get that your position at 2.8 was approximately 40.75, okay? So now let's go over to Q. What do we know about Q? Well, right here at t equals 0, particle Q is at position negative 90. That tells you that x Q, because now I'm on Q, right, of 0 equals negative 90. All right. You know VQ of t, right? It was given to you. So you have that. So it's the same concept, right? If you have a derivative and you have initial condition for the function, then you should be able to write that as an integral function. So in other words, xq of t is going to equal the integral from something to t. What would it be? It'd be from 0 and then negative 90 out here of v q of t dt. Okay, so now if I want the position at 2.8, it would be negative 90 plus the integral from 0 to 2.8 of vq q of t dt. Now, again, this was a calculated question, so you were expected last year on this question to do this in your calculator. So when you do this in your calculator, you're going to get 45.937 dot, dot, dot. Okay? How could they ask you a question like this on your test? They'd have to give you a function right here that you can integrate by hand. Okay? So now if we're trying to figure out the distance between the two particles, then just subtract these two values. All right. So if I did that, 45.937 minus 40.75, that's going to equal 5.187 meters apart. Okay. And there you have it. All right. So pretty good stuff there. So awesome question. Rewatch this video as many times as you have to get the concepts. If you got this wrong the first time doing it, watch the video, then redo it without watching the video, and then watch the video again. All right. We're only doing one question a day here, guys. So you should be able to do that so that we can rock and roll on this exam. So if you have not done this question yet, because some of you are waiting for the video still, please stop doing that. Get it done, get caught up over the weekend, and then we'll start with another question on Monday. Hope you're all good and safe. Take care.